All right. So as I said, we are going to look at induced dipole attraction. So what I've drawn is two spheres. Okay, these spheres signifies a molecule, or for our purpose of discussion, yeah, I'm going to take it as, let's say this is one atom, let's say this is another atom. So how is induced dipole attraction occurs in an atom? So once you understand how it occurs in an atom, you can extend this idea to a molecule. Basically the same thing. A molecule will be basically two atoms, what you call linked together by a covalent bond. It's just an extension of the idea. All right. So let's say in this atom, you have a nucleus. So I'm signifying the nucleus like that. And then you must know that you have what we call electron shells like that. Okay. You have electron shells in every direction like that, and then you have electron shells like that. Okay, so electron shells are around the nucleus. So this is just a spherical boundary. So you have electron shells. Okay, so let me simplify that idea again. So your understanding must be there. So this is the nucleus. So you have electron shells running here, your electron shells in direction, in all that direction, and electrons are moving around the nucleus in this sense. The same thing you have here as well. Okay. So my point is, point number one to note is electrons move randomly. They move randomly. Now, because they move randomly in the electron shells, that's very important. Now, what's your understanding of randomly? Randomly means there's no fixed pattern. There's no fixed pattern, there's no fixed time and all that. So they just haphazardly move around the electron shell. Of course, they have a spin number. Of course, they either move anti-clockwise, another set of electrons move in clockwise direction. But the point is they're moving randomly. So because of this random movement of electron, you will bound to get what we call non-uniform distribution of electrons around the nucleus. All right. So a typical example of this, a typical non-distribution electrons around the nucleus is within this atom, at a certain point of time, you'll have too many electrons on this side and too few electrons on this side. Go again, too many electrons on this side, too few electrons on this side, due to these two effects, due to the electrons moving randomly, and as a result of that, non-uniform distribution of electrons around the nucleus. So when you have too many electrons on this side and too few on this side, you will have on one side distribution of more negative charges, and the lack of electrons will give you positive charges. So as if your electron is divided into, your atom is divided into two. So this will have partial negative charge, this part of the electron. So it's best for me to put beside that. So this part of the electron will have partial negative charge. This will have a partial positive charge. All right? Okay. Now, it doesn't happen to this atom. It only happens to this atom. So let's say it happens to this atom. That means while these atoms moving randomly, suddenly at one point of time, non-uniform distribution of electron occurs to this part of the electron. So there's more electrons on this side that makes it negative charge, a partial negative charge. Lacking of electrons in this charge, that means partial positive charge. Now, this atom has an effect of causing an induction of this atom. And that's the meaning of induced dipole attraction. That means initially it is this atom which is dipole. Dipole means you have one pole negatively, partially negative charge, another end, one end partially negative charge, another end partially positive charge. This means dipole. So you have already got a dipole in this atom, not in this atom, but in this atom, due to these two effects. But this atom will then cause an induction because these are neighboring atoms. So this partial positive charge will then cause the electrons of this one to be pulled towards, will be attracted towards this. So this one, that means non-uniform distribution did not occur yet. Electrons are moving randomly because not all the time or not immediately you'll have non-uniform distribution. It is after some time of random movement you get that. So it is not occurred here, but because this is already been already having a partial positive charge, it will be able to attract the electrons in this atom and thereby causing causing non-uniform distribution of electrons in this atom and lack of electrons on this side. So in other words, this charge becomes partially negative charge. This becomes partially positive charge. But the point to note is this partial negative charge was induced by this fellow. That's the meaning of induced dipole-dipole attraction. And this, imagine, goes three-dimensional direction. It goes in all directions. So when one becomes dipole-dipole, the rest are induced to become dipole-dipole. And throughout in a three-dimensional fashion, you have what we call an induced dipole-dipole attraction. The attraction between these two. The attraction between these two. The attraction between these two. This is what we call induced dipole-dipole attraction. Induced dipole-dipole attraction. That's why it's called induced. And this is projected and extended throughout the three-dimensional lattice of the molecule. And it is pretty strong. All right. But overall, as I said, relatively it's weak, but it extends in all directions there. And this is caused by the induction of one atom over the other. All right. I hope you all understand this. So do you all understand it? Now, how strong, or let's look at the strength of this dipole-dipole attraction. Okay. So obviously, always learn to have a good analytical skill. All right. When you go to in the analytical skill, you learn to go straight to the root cause of this induced dipole-dipole attraction. The root cause of this induced dipole-dipole attraction, if you are able to focus it, if you are able to label it, will be your electrons. They are the root cause. So the electrons moving randomly and giving you this situation is the root cause of the dipole-dipole and subsequently induced dipole-dipole. All right. So if you fall back to this, and you know that all electrons move randomly, but if I have more electrons moving randomly, just imagine you are standing in the center and there are 10 people moving around you, just moving around you randomly. Okay. The chaoticness or the randomness or the non-uniform movement of these students will be more pronounced if you have more students moving around you. Let's say now 50 students moving around you, okay? Compared to 10 students, 50 students moving around you will give you a greater non-uniform distribution than 10. Therefore, from here we know the induced dipole-dipole attraction, it will be more strongly exhibited by atoms with more number of electrons per atom. So that's the main factor. So the main factor that determines the strength is determined by number of electrons per atom. So bigger the number of electrons, stronger is the induced dipole-dipole attraction. Induced dipole-dipole attraction. Induced dipole-dipole attraction. All right, this is evidenced in halogen. If you look at halogens, you look at fluorine, you know fluorine is a gas. And then you look at chlorine. Chlorine is also a gas. If you look at bromine, bromine is a liquid. All right, and if you look at iodine, iodine is a solid. So it is also, you are also required to explain how is that. Look at the physical states. Why is it as you go down, all right, the group 17, all right, the physical state of halogen from gas transforms to liquid and liquid becomes a solid. Why is that so? Now you are in the position to explain. So you can say that the intermolecular forces, because the physical state must be related to melting points. The physical states of these substances must be systematically related to the melting point, and melting point must be related to the strength of the intermolecular forces. So let me make that point clear first, okay? So the physical state, all right, the differences in the physical states must be related to differences in the melting point, which must be related to the differences in the strength of the intermolecular forces. So let's go more in detail. So as gas becomes liquid and liquid becomes solid as we descend group 17, we expect the melting points to increase. So melting point of iodine is expected to be the highest. Melting point of fluorine is expected to be the lowest. Point number 3. So we say since the strength of the intermolecular forces directly determine the melting point, therefore iodine must have the strongest intermolecular forces and fluorine must have the weakest. We connect it that way. And now we explore into the intermolecular forces and we say that the intermolecular forces in all of them are van der Waals forces as a result of induced dipole-dipole attraction, because none of them have permanent dipoles. Fluorine, chlorine, bromine, and iodine. They all, the electronegativity of both of them are the same. So there's no permanent dipole. No permanent dipole. There's no delta positive negative at the initial part of it. You don't have that. Okay. Then how do you have what we call the intermolecular forces? How do you have the van der Waals forces? That's where you attribute this to induced dipole-dipole attraction. So the electrons in fluorine, just like that, move randomly around the nucleus of the fluorine in the fluorine atom. So there will be non-uniform distribution of electron, causing one end of the fluorine molecule to be partially negative charge, the other end partially positive charge, and this one fluorine molecule then induces the neighboring induces the dipoles in the neighboring fluorine molecules, and this is extended throughout the three-dimensional structure of the fluorine. Now, since it's a gas, it doesn't have the three-dimensional regular structure, but just the idea only I'm talking about. Okay, and that goes on to the chlorine, okay, and bromine and iodine. But why is the intermolecular forces in iodine the strongest? If you look at the proton number of iodine and compare with the proton number of fluorine, you will find that the proton number of iodine is much bigger than bromine, much bigger than chlorine, much bigger than fluorine, and hence the number of electrons. Now we are coming to that. Number of electrons per atom increases as we go down group 17. Increases, and therefore the bigger the number of electrons, stronger is the induced dipole-dipole attraction. All right, that is why the intermolecular forces, which is this, is strongest in iodine, so strong to the extent that its melting point is higher than room temperature, all right, and making it a solid at room temperature. That's our explanation. Okay, so I hope you have understood that. Okay, now any questions you can ask me now.